This video clip is to help with part 3 in the titration lab, question number 18. Question number 18 is something to help prepare for how to process the lab data that would then be used in questions 26 to 41 in the lab exercise using your own data. This is using some data that would be similar to what you've collected in the lab exercise for part 3. You've generated your own titration curve for your weak acid titration, and you have data such as how many grams you weighed out of your weak acid, how much water you dissolved it in, and also from the graph we can get our initial pH and equivalence point pHs. Our initial pH would be right here when all that's present in our solution is HX and water. It appears right here that our pH looks like it's about 2.6. So we'll jot down our initial pH to be about 2.6. Milliliters added at the equivalence point, we want to go to the midpoint between our vertical break here. This falls right there in the middle of the vertical portion of our titration curve, and it would appear that our volume is 25 milliliters at this point of any. Next part says to eyeball right about our halfway point. The halfway point would be when we've added 12.5 milliliters, given that it took 25 to get to the equivalence point. We now have our information we need for the start of the problem. Our initial pH is about 2.6. We added 25 milliliters of base to reach our equivalence point, 12.5 milliliters of base to reach our halfway to the equivalence point. Now we know that our base concentration is 0.1 molar, which gives us a known ratio of 0.1 moles sodium hydroxide to 1 liter. We've established that we had 25 milliliters of base added to reach the equivalence point. We can use a proportion to find out how many moles of base were added to neutralize the acid. Calculating X, we find that we added 0.0025 moles of sodium hydroxide to reach the equivalence point, which the equivalent point gives us. The equivalence point is when moles of acid and moles of base are equal. So we also now know that we had 0.0025 moles of acid that got neutralized by the time we reached the equivalence point. Molecular weights measured in grams per mole. We have to know two things, grams and moles. We weighed out 0.45 grams of weak acid, and we know 0.45 grams is 0.0025 moles of weak acid. Setting up a proportion, we know we have 0.45 grams of HX present in 0.0025 moles of HX. That'll allow us to get how many grams are present in 1 mole. Solving, we get 180 grams per mole would be the molecular weight of this unknown weak acid. Our concentration is measured in moles per liter. We now know how many moles of acid we have, so we can get our moles of acid. The volume, we dissolved our acid in 90 milliliters of water, so we know both our moles and liters to give us our initial concentration. We can set up a proportion with our moles of acid, 0.0025, our volume of our acid solution, 0.090 liters, which is our 90 milliliters of water used to prepare the acid solution. Solve for X moles per liter. That'll be our initial concentration of our acid solution. We find that the initial concentration of our acid was 0.028 molar. Our pH of our acid solution initially from the graph we can see is roughly 2.6. This will allow us to calculate the H3O plus concentration in our weak acid solution. Calculating our H3O plus, we find that the H3O plus is 2.51 times 10 to the negative third molar prior to starting the titration. The next part asks us to calculate the Ka value for the weak acid. For this, we'll utilize the Rice strategy. Let's start by writing the hydrolysis reaction for the weak acid in water. Earlier, we calculated the initial concentration of the acid. That's so we can utilize this for the initial value in our Rice strategy, the 0.028 molar. Initially, before the acid reaches equilibrium, we'll say the H3O plus and X minus are 0. We determine the H3O plus concentration from measuring the pH of the solution prior to adding any NaOH. Using our at equilibrium values and our Ka expression for our weak acid, we can substitute in the equilibrium values and now calculate our Ka value. Calculating, we get 2.47 times 10 to the negative fourth for the Ka value of this weak acid based on the data we've collected. Now, at the equivalence point, we know that the moles of acid is equal to the moles of base that we added to neutralize the acid. Once the acid has been neutralized, the only thing present at the equivalence point is now salt, NaX, and water. All of the acid that was originally present has now been turned into salt. So what we can now say is that the moles of salt is equal to the moles of acid, which is equal to the moles of base that were added to neutralize the acid. What's happened by the equivalence point is all of the acid present has turned into salt. So however many moles of acid were originally present is now how many moles of salt are present in the solution. Consequently, we can say we have 0.0025 moles of salt, NaX, present at the equivalence point in our solution. To get the volume of the salt solution, it's a combination of the volume of the acid that was originally present plus the volume of the sodium hydroxide that converted the acid into salt. The volume of our acid is given by dissolving the acid in 90 milliliters of water, so we have 0.090 liters of acid. The volume of our sodium hydroxide is how much sodium hydroxide we added to reach the equivalence point, which now has created a salt and water solution. That's 0.025 liters. Adding the two together gives us a volume of our salt solution of 0.115 liters, present at the equivalence point. To get the concentration of our salt solution, once again, concentration is moles per liter. We need to know two things, the moles of salt and the liters of salt. We just determined the volume of our salt solution, and the moles of salt present is equal to the moles of acid that were originally present in the solution. We can now set up a proportion. We know we have 0.0025 moles of salt present in 0.115 liter. That'll give us X moles of salt present in 1 liter, which would be the concentration of our salt solution at the equivalence point. Solving, we get a salt solution that has a 0.0217 molar concentration for our salt, NaX, present at the equivalence point. At our equivalence point, if we extend over to our axis, it looks like our pH at the equivalence point is roughly about 9.3 would be our pH at the equivalence point. If we know the pH is 9.3 at the equivalence point, our pOH would then be 4.7 at the equivalence point. We can use the pOH in the relationship pOH is negative log of the hydroxide concentration to calculate our OH concentration by using anti-log negative 4.7 will give us our hydroxide. Calculating the hydroxide, we find our hydroxide concentration is 2.00 times 10 to the negative fifth molar at the equivalence point. Looking at our titration curve, once again right here at the equivalence point, all that's present is NaX and water. Now the Na plus ion is going to be a spectator. That'll do nothing. But the X minus can go through a hydrolysis reaction with water to generate weak acid molecules and also hydroxide ions, which will cause our solution to become basic. We can use this hydrolysis reaction for our salt solution to calculate the Kb value for our X minus ion. We can set up and use the Rice strategy with the hydrolysis reaction for our salt, which is what's present at the equivalence point. Earlier we solved for the concentration of the salt solution to be 0.0217 molar. That's the initial concentration of the salt in our hydrolysis reaction. We also use the pOH from the equivalence point to get our OH concentration. The OH concentration, because this is a 1:1:1 ratio, allows us to get our equilibrium value for all three chemicals, which we can now plug into our Kb expression and solve for the Kb value. Solving for our Kb value, we get 1.85 times 10 to the negative eighth would be the Kv value for our X minus, which is the conjugate base of our weak acid HX. The next question, we'd identified that the halfway point to our equivalence point is 12.5 milliliters, which is half the volume necessary to reach the equivalence point of 25. This gives us a very unique and special point on a titration curve. From our graph here, it would appear that at halfway to the equivalence point, our pH is about 5. Now, at halfway to the equivalence point, there's a very special and unique arrangement of salt and acid present. Now, at the equivalence point, all that's present is salt and water. Initially, all that's present in the solution is weak acid and water. At halfway to the equivalence point, what we have present here is half of the acid's been neutralized, and the half of the acid that's been neutralized is turned into salt. So at this point, there's a ratio of 1:1 of HX and salt ions, in that the half of the acid that's been neutralized has become salt, and the half of the acid that hasn't been neutralized is still acid. So the amount of salt ions and acid present are equal to each other only at this specific point where we're halfway to the equivalence point in our titration. What happens at this very unique point then is because the HX and X minus are in the 1:1 ratio and equal to each other at the halfway to the equivalence point, the X minus and HX will cancel out. So at this unique point in the titration, the Ka value is equal to the H3O plus concentration. Because we know our pH is equal to about 5 at this halfway to the equivalence point, our H3O plus concentration is 1 times 10 to the negative fifth. So using this strategy where the H3O plus is 1 times 10 to the negative fifth, that'll also give us our Ka value. This is unique and specific only to this point where we're halfway to the equivalence point on our titration, where the Ka value is equal to the H3O plus concentration.